Man has always gazed at the night sky in awe and wonder. How far? Is space limitless? Is man unique? Today, we can peer far into the depths of space and see some of the many millions of island universes we call galaxies. Were they all created in a moment of time, the fragments of a tremendous explosion? Or is creation continuous in a universe that had no beginning and will have no end? These are the problems the cosmologists ponder as they attempt to grapple with the infinity of time and space. Who are these people? Tonight we meet Fred Hoyle of Cambridge University, the founder of the steady state theory. Hermann Bondi of London University, the secretary of the Royal Astronomical Society. At Jodrell Bank near Manchester, we ask Sir Bernard Lovell if astronomy's latest tool, the radio telescope, can decide between these rival theories. Stephen Black questions these leading cosmologists. But first he went to Arizona, to America's most modern optical observatory, perched 7,000 feet up on the summit of Kitt Peak. There, in beautiful wild country overlooking the Sonora Desert, he talks to an internationally famous husband and wife team of optical astronomers, Dr. Margaret and Geoffrey Burbidge. Although both of them are British, they've been living and working in the United States for the past 10 years.
Dr. Burbidge, why did you come to America?
Well, the telescopes, first and foremost. There are these beautiful telescopes here. The one that we worked with first of all was the McDonald telescope, 82-inch telescope in southwest Texas, and then we did some work at Mount Wilson. Most recently we've been working at Lick Observatory, where there is a very fine new telescope, 120-inch. It's a beautiful instrument. The observations I get with that, I just... it makes me wish that I'd had access to this for very much longer. It's a wonderful telescope. Then we have here at Kitt Peak, we have the new telescope and the 84-inch telescope, and then there is a still bigger telescope, 150-inch, that's underway. All these things, all these observational facilities, but more than that, I think it's the climate of not the weather climate only, but the interest in astronomy, the fact that you can talk to other people who have exciting new ideas in your own field. You can exchange ideas. You're not working in a vacuum so much as you are in England.
I feel as if we're on the edge of nowhere. I also feel the telescope looking out into nowhere. How far can it see?
Well, that's an awkward question, because astronomers don't like to measure distances in miles. It's much easier to think of distances in terms of the time taken for light to travel from any object in the sky to us. Well, I don't know. How far would you say?
Oh, perhaps 500 million light years or 1,000 million light years, or perhaps even further, depending on what kind of observations one is trying to make.
Can we just clear up this point about 500 million light years?
The distance that light would travel in a time of 500 million years.
So that anything you see coming from a star 500 million light years away is 500 million years ago.
That's right, that's right.
Yes, and of course, when we talk about stars, we're thinking of stars much closer to us, stars in our own Milky Way. The things that are these vast distances that we make observations of are separate Milky Way systems or galaxies, island universes, or whatever you like to call them.
I think we ought to get all these points cleared up. You talk about our own Milky Way. Now, up there's the sun. That's the center of our solar system.
Yes.
And then that belongs to?
Well, that belongs to, the local group of stars that we call our solar neighborhood, which is part of the Milky Way system that you see if you look out in a dark night, and that you see the Milky Way, which is made up of myriads of stars. And these are shaped in a kind of a flat disk, more or less disk shape with a bulge in the middle. So we're situated about 2/3 of the way out from the center, at least the sun is. And when we look through the thickness of this, we see the Milky Way. And if we look in the other direction, out of the out of this mass of stars and dust and gas and so on, we can see other Milky Way systems right outside our own.
These are the galaxies?
Yes.
So we belong on Earth, which goes around the Sun, which is
Yes.
one in millions of suns in the Milky Way, and then there are millions of galaxies beyond the Milky Way.
Yes, that's
Now,
right.
how does this space shot program fit into this? How does this Sputniks, the space traveling, how far are they going to be able to go out into this space?
Oh, not really outside the solar system, I should think.
And you as an astronomer, how do you feel about all the money that's being spent on this sort of thing?
I think we get rather angry when we think of the money that's being spent on these sort of things, and what we could do in ground-based astronomy by putting new telescopes in the southern hemisphere, for instance, telescopes of the size of the 200-inch telescope in California. We could do this for a fraction of the money that's contemplated in these sort of things, and the problem of putting a man on the moon and so on.
What sort of questions would you answer then if you had these telescopes?
Questions of the life study, the life history of galaxies, the stellar evolution, how stars form, what happens to them after they've formed out of the gas and dust in our galaxy, how they build the chemical elements in their interiors, and how these get mixed back into our galaxy and form the building material for later generations of stars. The kind of things that are going on in the very central regions of other galaxies than our own. I think these are some of the exciting things that we'd like to do with more telescopes.
What are the ideas on this at the moment? What are your ideas on it? How do stars start?
Well, maybe a question of star formation is it?
Well, how stars are actually condensed out of the interstellar gas and dust, the material between the stars, is still not very clear. Some very fundamental work was done by Sir James Jeans in 1900. And in some respects, we have not advanced too much in our theoretical knowledge. That is, it's very easy to prove theoretically that stars can never form. But, of course, we know that they did form. Perhaps a very large number of stars formed in the early history of our galaxy. And we also know, quite by very good arguments, that stars are forming continuously. That is, we are able to determine the ages of some stars, and we know, for example, that some of the brightest stars that we can see, and some of the most massive, some of the heaviest stars that we know, can only be something of the order of 1 or 2 million years old. The general arguments show that some stars are as old as 10,000 million years in our own galaxy. We don't really know anything about the ages of stars in other galaxies. But this means that we have established that star formation has been going on continuously from a period perhaps some 10,000 million years ago, right up until the last million or so years, which in astronomical terminology means now.
Of course, this raises some of the fundamental questions of cosmology as distinct from astronomy. I mean, when you talk about things forming in space, stars starting, you raise questions as to what starts them and why and how it all began.
Yes.
Well, one can, of course, put it this way. On the other hand, one can take a more limited view and say that one is discussing the history of our own galaxy. And if one wants to relate the early stages in the history of our own galaxy to the early stages in the history of the universe, if one believes in such an evolutionary cosmology, an expanding universe expanding in a big bang, or from an essentially a point source, then perhaps it is of cosmological interest. But we're not sure of this, because it's also entirely possible that new galaxies are forming even now. And so to date the history of a galaxy, and the age of a galaxy from the time, from the beginning of creation in some evolutionary cosmology, is really not necessarily correct.
Dr. Margaret, would he be trying to avoid my question?
Maybe he is, because I think we all are interested in the cosmological problem, or whatever you like to call it. We can't help. It ties in with our philosophies and so on, and we can't help wondering about it, even if our observations don't get very far towards settling anything.
Oh, when he uses the word creation, he starts a whole train of thinking.
That's right, yes.
The doctors Burbidge and Burbidge wouldn't be trying to avoid using the word God, perhaps, would they? They talk about creation, they talk about a beginning, but we never get back to the fundamental problem as to how did it start. Do you believe it possible that it started without some act of creation?
Well, I just feel I don't like to tie myself to any particular belief. I just feel agnostic about this, that I believe in a spiritual side to the universe, but I don't believe in any formal theologies or anything like that.
Dr. Burbidge looks very cynical on this, Dr.
Well, it's you who call this a fundamental question, you see.
Well, when you introduce the word creation, you raise the question.
No, it's the connotation that you put on the word creation. I think that is really...
Well, creation suggests a creator, doesn't it?
I think it presumes a creator, but perhaps not, Dr. Burbidge. Can you...
No, it presumes that there was some kind of an act, but one is not. Now, for example, continuous creation. In continuous creation, what is being talked about here is the appearance of matter to replace the matter which is expanded away. And until we have some kind of a physical idea of this process, I don't think we can attach too much importance to the whole theory from this point of view. Now, you talk about the act of creation in an expanding universe which started with a Big Bang. Well, here again one goes back to conditions, or one is forced back to conditions under which the properties of the fundamental particles and the properties of the nuclear properties of the system become very important. And so I don't want just to sweep this all up, this tremendous amount of physics which we don't understand, into the one word creation and then immediately say God, because that to me is the easy way out.
How did you two meet?
Well, we met at the University of London. I was working at the observatory there, and the University of London was where I got my degree, and I was going to some lectures on the upper atmosphere, and he was working for his PhD there, and we were going to the same lectures, and that's how we met.
And you got a little girl?
Yes, yes, she's 6.5 now.
Do you introduce the idea of God to her?
Yes.
That's interesting.
Well, I think you have to. Children that age can understand philosophical problems. You have to try and make things simple, and introduce the harder concepts, I think, as they want to know about them.
What's the most exciting thing that's happened to you since you started working in astronomy?
Well, I think the most exciting time was when we were working in theoretical work on the origin of the elements, but a number of separate exciting things that I can't think of one now, but the excitement of after you've worked one bitter cold night, a whole long night, 8 hours or so observing on one object, and then you finally develop the plate and you find something you didn't expect there, some new thing, or you've actually brought up something on the plate that you were hoping for vaguely but didn't know whether you'd get it. And that's a wonderful moment.
Professor Hoyle, when I was in Arizona, Margaret Burbidge gave me this photograph and said that she thought that it was her view that this was an actual photograph of the creation of a galaxy some 130 million years ago. What's your view on that?
Yes, I know this one quite well. It's a real beauty, isn't it? I'm not too sure. It could be, that's perfectly true, but there's a sort of group of stars in here that makes you sort of wonder whether it really is a new galaxy that's formed. I should say there are quite a lot of chaps like this, and I think it's probable that some of them are newly forming galaxies, but I wouldn't myself like to go quite as far as Margaret, probably because I've got more at stake than she has in this matter.
What have you got at stake?
Well, the implications of new galaxies forming are pretty striking for the type of cosmology that I've been associated with. As you probably know, there are two forms of cosmology, what has been spoken of as the Big Bang and the steady state. There are actually many Big Bang cosmologies, and they all have the property that the universe is supposed to have started at a particular moment. And quite early on in the game, all the galaxies are supposed to have formed, and there shouldn't be, therefore, any of these fellows like this, possibly, forming at the present time. But on the other view, the one I've been associated with, the galaxies must be forming the whole time, so that it is a definite prediction of the second type of theory that these sort of events should be taking place.
You reject this Big Bang theory, this concept of a beginning and an evolution and it going on.
Well, I do, and I always have done, for reasons that you might think are not altogether astronomical. I've always been impressed by the views of people who argued that the plants and animals on the Earth, all this complexity was due to them being suddenly made in that way. We know now, since Darwin, that this is completely wrong. We had just the same story with the chemical elements. People said, well, all the different elements like sodium, oxygen, the carbon in our bodies, and so on, had always been that way. But we know this isn't true, that the oxygen that you and I are now breathing was actually made inside stars, and that the iron in our cars was made inside stars. So that the lesson that one learns from these cases is that one doesn't impress on the universe its properties in the start. Things develop out of the basic laws of physics. And I believe this must be so for the universe as a whole.
Then how is it made?
Well, I don't think it was. I think that what we can show quite definitely is that individual particles have got to be made. If I could perhaps sort of demonstrate the point of view that I have and the point of view that the other chaps have got. Suppose I draw along here a direction, just one direction to represent space.
That's the three dimensions of space.
Yes, all in one. And this way, time. Now, what the Big Bang people say is that the particles, each individual particle, is a sort of line on here, and they all start at the same moment of time. But that's to say, these are the beginning points here, but they don't give any sort of physical description of what causes them to begin. Whereas I think what one has to do is to give a correct mathematical physical description of what one means by the beginning of a particle. And I think when you do that, you don't find that they all begin at the same moment. I think you find that they are scattered with ends at different times, that they're all mixed together. This is what I find. And that when you give correct mathematical description to this, you'll find that the universe itself didn't have to have a beginning.
These particles then are at the ends, which I would call the beginnings of your lines. These particles are in fact being created out of nothing.
No, this is not quite the case, not out of nothing, out of a field. This is the essential feature of the mathematical description of the creation process, that one has to think in terms of what a physicist calls a field, and maybe I can put it to you in the following way. I have an electric circuit here, and I press a switch, and a current flows, and a little magnet over there sort of moves around. So some form of influence has travelled from the left here to the right there. Similarly, of course, you could have a torch here, and you could flash a message across or some light across, and you could receive it over here. In both cases, an influence has travelled from left to right. And if you ask the further question, what causes that influence to travel? It is, in physical terms, a field. There is the familiar magnetic field, which is one case. There is the electromagnetic field that carries the light from the sun across all the space from the surface of the sun to us here on the Earth. There's a gravitational field. Now, there's a whole family of these sort of chaps, these fields. And what was done in order to represent the creation of matter was to take one of this member of the family, perfectly straightforward and respectable member, and to see that it could be used to represent the creation of particles of matter. And so the normal mathematical methods were used, and the normal type of mathematical description was also used.
So that a particle is formed, and then in some way, through this field, the information of that particle being formed?
Yes, what I call the end, or as you say, the beginning of a particle over here, sends out a signal which can be received over here, And the effect of all such signals can be to make another particle here, appear here. This is the sort of way it works.
And this is continuing the whole time. At what sort of a speed?
Very, very slow by ordinary standards. If we take a room like this, well, I haven't done the actual calculations, but I would say to produce just one atom here would maybe take 10,000 years or so.
This would be why no one has ever discovered the creation of an atom in a laboratory experiment.
Yes, indeed. It would be extremely difficult, if not impossible, to find the rare atom that would appear inside the physicist's lab. I think one has to reckon that if you try to do all your physics in a terrestrial lab, there may be some things that you wouldn't find. I suspect if it wasn't obvious that there was such a thing as gravity, the terrestrial physicists would never have found it. If, for instance, all physics were done out in space in a freely falling lab, I don't think the physicists would have suspected the existence of gravity. So I don't think it's necessarily surprising that there might be effects that one can't find or not very easy to find in the lab, in the ordinary lab.
You have here in Cambridge Professor Ryle, who is a radio astronomer, and as I understand it, he made a study of the radio stars and claims to have proved your steady-state theory to be wrong.
I still take the same view today. I think we cannot know whether there is a contradiction with the theory until we know exactly what these radio sources are. And I think it's not going to be very long before we do know. I think the big breakthrough has been made in the last months. And indeed, only yesterday I had an exciting letter from my colleagues in Pasadena that I've been working with on this exact problem. And although I'm a really shocking correspondent, I immediately dashed off the reply by yesterday afternoon. The whole thing is really very, very hot, and I think we shall begin to clear up this issue of what radio sources are, maybe not within months, but within years, and then it will be much easier to evaluate whether it really is like this, a contradiction, or whether there isn't a contradiction.
Well, and how did you set about proving your theory?
Well, one way was to decide whether the chemical elements, the oxygen and nitrogen that's in ours, are made inside stars, because this is what the theory required, and this is something that could actually be checked by direct observation. And I think it's this that Margaret Burbidge was reporting to when she said was referring to when she said it was one of the exciting moments, really chasing this down, and it was chased down, but it took 10 years to do it. It takes quite a while when you're really tackling these things before you become sure. I think my objection to Ryle was that he was too sure too quickly.
Can you remember a moment in time when you first saw your theory, when you first saw the possibility of supporting this mathematically and proving it?
I can remember it pretty well. There were two things that happened towards the end of 1946, just after the war. One was a remark to me from Professor Piles that if I was concerned with building atoms inside stars, perhaps one ought to think of how atoms themselves were made. This was after a talk I gave in Birmingham. Another was a remark of Tommy Gould's. He came in one day when Hermann Bondi and I were sort of working on quite a different problem and said, what if the universe is like a sort of loop of film that goes round endlessly? Well, nothing much happened, because it was pointed out to Tommy at that time that in order for this idea to be right, it was necessary for matter to be created. And because this seemed like an objection, it was dropped. And that's why it took quite a long time to make any further steps. It wasn't, in fact, until about 16 months later that I saw how one might give mathematical expression to this idea of a creation of matter. And I remember, I think it was on the 10th of February 1948, that one evening I got down and really got the equations on paper. I remember I had them somewhere about 10 o'clock in the evening, and I sat up till 3 in the morning, and by then I had the solution that I wanted.
What did you do at 3 in the morning when you'd found the solution you wanted?
Well, I suppose I went to bed. I'm a very good sleeper, and I suppose I was pretty tired at that stage, but I did spend the next 2 days working pretty hard and wrote my paper in the next 2 days.
You wrote the paper in 2 days?
In 2 days, yes.
And what did you do with it then?
Well, I sent it to the Physical Society of London, and after matter of a couple of months, they said it wasn't suitable material for their journal. Then I sent it to the Physical Review in America, and they said exactly the same thing. And finally, I did what I should have done in the first place, sent it to the Royal Astronomical Society, and it was published. But I perhaps should say that at that time, it was rather difficult to get papers published quickly, and that was the main reason why I tried the Physical Society and the American publication, because they were publishing much quicker than the Royal Astronomical Society.
How did you feel when the Physical Society and the American paper turned your paper down? What did you feel about that?
Oh, mad, to say the least. Very angry.
Angry with those around you?
Oh, not at all, no, with the journals.
How do you react to that kind of situation personally?
Well, I have a bad 2 or 3 hours when I could eat any number of carpets, and then it sort of passes off. But I am pretty shirty for a little while.
You must, of course, feel that this theory of continuous creation does away with the need for a creator or for a moment of creation in the past.
As regards an idea of a God, I myself don't think that the concept gets you anywhere at all. I don't think once you've used the word God, you know any more than before you used it. If you try to say there is some sort of coherent plan in the universe, I think I would tend to agree. But what it is a plan for, or what it is aimed at, I think we just do not know. I suspect that our brains just may not be in a condition where this is a soluble problem. I'm very impressed, for instance, by the fact that a mile or two off the shores of Yarmouth, there are fish swimming around there. They're only a mile or two away, but they're separated by hundreds of millions of years of evolution from understanding what goes on in Yarmouth. And I think it must be so with us in regard to many problems.
Given then that there are problems with which we cannot grapple, how then do you regard the existence of faith?
Well, faith is a very important quality. I would have said it was the most important of the three, charity, faith, and hope. And it is particularly important to the scientist in all his daily life, in the problems he is tackling and may solve. He must have faith that in making big efforts that he has a chance of success at least. In a sense, the whole of life, I would say, is an act of faith. And paradoxically enough, I would think it is the atheist who has more need of faith than the religious person. Your convinced Christian, surely he doesn't really need very much faith because he knows what the answer is. It's the chap who doesn't know the answer that needs the faith. Well, if I may just sort of summarize what I feel about this whole question of God and of science. You may remember that Jeans, in a very famous book and lecture called The Mysterious Universe, outlined the reasons why mathematics is so important in describing the world. And he ended by asserting that God was a mathematician. I would say his argument was pretty good up to the end, but I would say that he was quite wrong in bringing in God. What he should have said is that really mathematics is God. The basic laws of physics, insofar as we have any concept of God, is God.
Is this dish of the radio telescope where we're standing now really receiving information from the very edge of space, from the very edge of the expanding universe, Sir Bernard Lovell?
Well, the telescope here has certainly received radio waves from an identified source, which is so far away that its messages have taken something like 5,000 million years on their journey towards Earth. And this source is moving away with the speed of about half the velocity of light. The evidence is that the telescope has penetrated much further than that, but how far, we're not sure. The penetration, of course, to the ultimate depth of time and space which is demanded by the evolutionary Big Bang theory, is forever unapproachable, because as one penetrates further into space and further back in time, so the velocity of recession of the galaxies and clusters of galaxies which one is observing forever increases. And there comes a time when this factor, this extremely high velocity, would mean that they were in any case unobservable.
Do you feel that in the face of all this material progress, the vanity, the hubris, if you like, of the scientist is unreasoned? Or are you also tempted to think that we can find out all the answers?
Well, I see nothing in modern scientific discoveries, either in physics or astronomy, which enables one to dismiss the spiritual aspect in God, as Hoyle does. But of course, it's in cosmology, in astronomy, in this problem of the, particularly in the problem of the creation of the universe, where the issue appears in its most acute form. Although I think you see that we've reached an epoch during the last decade or so where there have been revolutions, particularly in astronomy, with the radio telescope and the space probe and the great discoveries with the optical telescopes, which have had the kind of impact on the subject which hasn't happened since the time of Galileo and then of Newton. And in that time, there was a very marked swing towards materialism. And the same thing is happening now. This sudden access to the remotest parts of the universe, it appears suddenly that the veil of the heavens are being torn asunder and everything is being revealed to us. Well, I think anyone with sufficient experience would realize that although, of course, at any time one has to have faith and one feels that the experiment one is doing now is going to give one the exact answer, this never does in fact happen. I have no sympathy at all with the kind of arrogance that the tools which we have at our disposal today are the ultimate means of the investigation of nature and will give us the final answers. I think this is not true.
Sir Bernard, it seems to me that the scientist's choice between the Big Bang theory and the theory of continuous creation is really entirely an arbitrary one, until somebody does some experiments or makes some observations to prove it one way or the other. Now, is this telescope going to help?
Oh, certainly. We think that it's penetrating so far back in time and out in space that it is giving us information about these regions which probably hold the key to this great problem. You see, the issue can be put rather simply in this way, that if the continuous creation theory is correct, then this implies that the universe has always been the same, however far one goes back into time past, as it is today. And therefore, if we penetrate to regions of space which are giving us information about the cosmos as it existed, say, 7,000 or 8,000 million years ago, then we should see the same kind of situation as we find in these regions of space and time which are closer to our own epoch. Whereas, of course, if the evolutionary theory is correct, if the universe began as in some sort of Big Bang, as it's popularly called, in the time of about 10,000 million years ago, then if we're penetrating to these regions, the universe will look quite different.
Does your work in astronomy lead you to believe in the uniqueness of man or the uniqueness of life in the universe?
I would say no, I would say the opposite was the case. You see, there are really two problems here. First of all, obviously, is the biological problem as to whether the life processes are unique. But first of all, may I say a word about the astronomical problem? Because if one's going to believe in the uniqueness of life, then one has to have a fairly good belief that the Earth is unique. And this was believed to be the case until quite recently. But now it seems unlikely that the Earth is unique and our own planetary system is unique. In fact, the modern ideas about the formation of planetary systems makes it seem quite certain that planetary systems, of which the one around the Sun is an example, must be of extremely frequent occurrence in the universe. Well, there are 10,000 million stars in the Milky Way. There are many trillions and trillions of Milky Way systems in the universe. So if you begin to put in the most colossal odds against any of these planetary systems having suitable, stable abodes like the Earth, you still end up with very, very large numbers of Earth-like abodes in the universe. And therefore, I would say from the astronomical point of view, the situation is fairly clear. That the Earth, or an Earth-like planet, is by no means unique. There must be many trillions of them in the cosmos. Therefore, the problem is really one for the biologists. If in spite of this, in spite of the plenitude of Earth-like abodes, has it been something which has led to the unique evolution of life as we know it? This, of course, goes back to the question as to whether the primeval organisms are distributed throughout the cosmos. And there again, the astronomical beliefs indicate there's no reason why they should not be. All that I would say is that the present investigations with the space probes may well give us the answers quite soon in the investigation of the planets. And there have, of course, been the very remarkable investigation of the organisms on the meteorites, which have been made during the last few years by the American scientists. So I would say that the modern tendency is to think that some forms of life may be quite widespread in the universe.
If terrestrial life isn't unique, Sir Bernard, doesn't this raise new problems in ethics?
Oh, indeed, very much so. You see, all the time so far we've been concerned with the problem of ethics on Earth, and now they have suddenly assumed extraterrestrial aspects. For example, take our modern ability to send probes to the vicinity of Mars and Venus. On those planets, there may be developments taking place, which it is extremely important from the scientific point of view they be investigated. And can we be certain that there is going to be any safeguard against the impact of a contaminated terrestrial rocket on those planets, carried out for chauvinistic reasons, which might inhibit forever the critical scientific investigations? And if so, then we assume the moral right to interfere with this environment. And then, of course, this very grave example of the explosion of the hydrogen bomb in outer space by the Americans. An explosion carried out in the face of opposition from the International Union of Astronomers, that no experiment would ever be done unilaterally which might alter the environment of the Earth. I must say that for the first time in my life, this event has shattered my belief in the inevitability of scientific progress. The explosion altered the particle environment of the Earth and has created so much radiation that in even certain parts of the radio spectrum, many months after the event, there is still the same intensity coming from the remains of the explosion as coming from the remote parts of the universe. So the problem is an extremely serious one. Therefore, I think that the problem in ethics have now assumed attributes, have now assumed extraterrestrial attributes. You see, it may be to explode a hydrogen bomb in our own atmosphere, may be human folly on a terrestrial scale, but to explode a hydrogen bomb in outer space is folly on a cosmical scale.
Professor Bondi, so far we've seen something of the tools used in astronomy, the optical telescopes at Kit Peak, the radio telescope at Jodrell Bank, and we've heard some of the views on the nature of the universe. There appear to be two theories as to the origin of the universe. One, the Big Bang theory, in which the universe has at least a beginning, and the steady-state theory, in which it has no beginning and has presumably no end. In either case, it is apparently an expanding universe. Now, to start with, what is the evidence for that?
The evidence for this is probably the most important set of observations in cosmology. It is that when the astronomer looks at the most distant objects, the very distant galaxies, he sees that the light from them has all the characteristics of light emitted by a body that's going away from us. He's not very good at estimating distances, but in as far as he can do it, moreover, the further away the body, the faster it is moving away from us. One might think at first sight that this means that we are at the center of something and everybody is rushing away from us as though we had the plague. But in fact, the situation is not like that. With a system like that, it has the very interesting property that it looks the same from wherever you are in it. We are going away from you if you sit on a distant galaxy, just as you are going away from us. And the whole system looks just the same to them as it does to us. So this motion of expansion, of things going away from us with a higher speed the further they are away, that fits in perfectly with the idea we have that if you look at the universe on a very large scale, then it's everywhere the same, then it's uniform.
Given then that the universe is expanding, with regard to its origins, with regard to the origin of the universe, do you consider it is reasonable in science to have two conflicting theories with only an arbitrary choice between them?
By no means. This is the real purpose for which one works, is to find ways in which one can test these theories. Perhaps I can enlarge a little here on the methods we generally use in science. The scientist, guided by what he knows, guided by the evidence of his days, produces a theory. And the purpose of this theory is to comprehend what is already known. But over and above that, beyond that, it is essential for the theory to make statements that can be tested by future experiments and future observations. The theory must stick out its neck. A theory that doesn't stick out its neck that way is unscientific. And what happens then when it sticks out its neck? Well, if the test goes against the theory, then clearly the theory has been disproved. And this is the one thing that we can ever say with any degree of certainty. For if the test goes for the theory, then it would be quite wrong to say that the theory has been proved. It merely is the task of the theory then to make further forecasts, to test again and again and again, stick out its neck so that it can be tested more and more and more. So the guiding principle here is disproof. Everything we say is uncertain. We know that from experience. Everything is subject to disproof. And if anybody asked me to specify what was specific about scientific work in general, it is this lasting, this definite uncertainty. We can never be sure of ourselves. We must always go on making statements that can be tested. And this, to my mind, is where the conflict with religion comes in. I do not believe that there is any real difference, any real serious need to expect a discrepancy between religious statements and the results of science. But it seems to me that the methods of science are in utter opposition to the religious point of view. Particularly when we consider organized religion, then we know as a fact that however sincere people are, however strongly they hold their belief, they are very likely to be wrong. We know that because there are many different religions in the world. And to a scientist, like me at least, it seems utterly absurd that somebody should say, I am a Christian, meaning thereby, and I believe therefore that all the Muslims and all the Hindus and all the Buddhists are all wrong. Or any other religion which says just the same thing. Of course, I have no objection to somebody having a private view. We all have our private views. We all have our private friends. But when organized religion, knowing as it must that it's very likely to be wrong, because there are lots of other people holding opposed views with equal sincerity and equal determination, when knowing that it might be wrong, it forces its views on others. That seems to me to be very wrong indeed. And this is not something that was buried with the Middle Ages. This is something that goes on here and now.
Nevertheless, don't you feel, Professor Bondi, that at times the choices of science, particularly the choices of the astronomers and the cosmologists and the theoreticians in your field, are made on very frail evidence, very frail scientific evidence indeed?
I entirely agree that much of the evidence we work on is frail evidence. This is all the evidence we've got. We all know people who say in daily life all the time, but I can't make a decision until I've got all the evidence. And we know that these people never will make a decision because they never do have all the facts. This is not the way one goes on in science. One makes the best with what one's got, It may be very frail evidence. In cosmology, it certainly is frail evidence. But with that, we try just to see 1 inch further.
All right then, Professor Bondi. What do we know for certain and what do we not know?
Now, I think the most important thing that we know now as a result of all this work is the origin of the elements. As you know, hydrogen is the simplest of all the elements and by far the most common one. And all the other elements, the heavy elements as we call them, oxygen, carbon, iron, copper, uranium, the whole lot of them, people have thought for a long time that they must somehow have been built up from this simple elementary hydrogen. But the question is, where were they baked together to form these heavy elements? For a long time, they thought that there was no place in the universe as we know it that was hot enough for this to happen. And so people thought that they had to go back to the early stages of the universe, the Big Bang, when everything was very dense and very hot, and that then the hydrogen fused into the heavy elements. Of course, this idea is wholly unacceptable to those who hold with a steady-state theory. You remember that theory says that the universe is unchanging. If ever there were any factories for making heavy elements, there must be some such factories going now. And this was the inspiration that led to the work of the last decade by the Burbidges, Fowler, Hoyle, and several others, trying to discover whether there were not, after all, factories now making heavy elements. This was an attack from 2 sides, from the nuclear physics side, to discover what the conditions were that were necessary to make these elements, and from the astronomical side to discover where these conditions were realized. And the work was extremely successful. First of all, they discovered that there was a whole class of stars, not perhaps the most common or garden star, but not an uncommon kind of star, where most of these elements were baked together. And then they were able to work out from their astronomy not only that all these elements were produced, but in what ratios they were produced. How much uranium should there be to how much iron? How much carbon to how much oxygen? And so on. And the results of these calculations are embarrassingly like what we know from observation to be the different ratios of these different elements, how common or uncommon they are. Now, this strikes me as an extraordinary success, to be able to work out all this from what one knows by looking at the stars. This, I think, is the greatest achievement, and it is one that was inspired by the steady-state theory. It may well be that the steady-state theory will be shot down and nobody will think about it anymore. But it has earned its place in the history of science already, because it was the steady-state theory that inspired this most important and successful work. Second thing one knows about, of course, is the expansion of the universe. But perhaps one is not quite so sure here. Beyond that, there are theories, and we've talked about them, and there are tests that can be made, but one can't speak of definite knowledge. And what is it that we don't know? Well, there's an awful lot that we don't know, but perhaps we realize to some slight measure how much there is that we don't know. And this, I think, is where we may be a little bit ahead of the Polynesians. Our theories we don't hold with such assurance. We know they are going to be modified, they are going to be shot down by observation. We've learned from experience that we can't trust any of these things absolutely. Perhaps the most important thing that we have learned is that however firmly one holds a belief, however sincere one is, however convinced one is, that is no guarantee of its correctness.